Let's start right now with the second hour from Lingrui on applications of the quantitative global theory. Lingrui, the floor is yours.
Okay, great. Thank you so much. Okay, today I will give the second talk about the applications of the global theory. Okay, this applications actually is there are three papers. So the first one is on the almost reducibility conjecture, and actually this paper can be found on arXiv now. This is the arXiv number of the first paper. And for the second paper, it is about the stability of the thematic problem. So as I said, the quantitative global theory has spectral applications. So we will mainly consider about the thematic problem and the sharp phase transition or entry-orbit phase transition for more general Schrödinger operators. So the second paper is on this line. So we will prove the stability of the thematic problem. And this paper, we will post this paper in 3 or 5 days later. Okay, this is the second paper. The third paper is about the sharp phase transition for the type 1 operator. And this paper, we plan to first finish the submission of the above 2 papers, then we will post the third paper. Okay, so now I will first talk about the almost reducibility conjecture. Okay, before I talk about the almost reducibility conjecture, I'd like to introduce, let's recall some basic concepts for Schrödinger operators. So in our last lecture, we talked about the Schrödinger cocycle. Okay, this is a map from T times R2 to itself. And for a cocycle, important concept is called reducibility. So reducibility just means you can find a map, a conjugate map. This map is analytic B such that the original matrix A can be conjugated to a constant one. So this is reducibility. But in many cases, the reducibility does not hold. So a weaker concept is called almost reducibility. Okay, this just means one can find a sequence of map Bn such that you can conjugate this map A closer and closer to a constant one. So this is almost reducibility.
Yeah, I'm sorry, Lingrui, Sylvius has a question.
No, it's just a silly question. Sorry, it's about the definition. The age is the same for all n, or is allowed to go to?
Yeah. This is some stronger version of reducibility. So H, if H here in this definition, H does not depend on n. But in general, one can also have some more weaker version of almost reducibility. You can choose this H depends on n. Okay, this is some stronger version of almost reducibility. Okay.
Thanks.
Okay, no problem. And actually, almost reducibility has many. This is a powerful tool to deal with spectral problems. For example, you can use it to deal with the contour spectrum problem. Even you can estimate the spectral gaps, or you can use reducibility and the localization argument to prove the arithmetic Anderson localization. You can also use it to consider the Holder regularity of the Lemma exponent, also the absolute continuity of integral density of states. And even more, you can use it to prove ballistic transport or exponential dynamic localization. Anyway, okay, now let's turn to the almost reducibility conjecture. As I said yesterday, the almost reducibility conjecture is some conjecture about subcritical cocycles. So now let's recall that we introduced yesterday. We introduced a concept called acceleration. Okay, this is the acceleration, and this conjecture is related to the zero acceleration. Just means in this. So if we consider the picture of this L epsilon E, if there is a flat piece, then the acceleration equals to 0. So the almost reducibility conjecture says that if there is a flat piece in this complexified Lemma exponent, if and only if the corresponding cocycle is almost reducible. Okay, this is the for almost reducibility conjecture. Actually, if this L epsilon E is larger than 0 for epsilon and is stable, then this is the uniformly hyperbolic case. And in this case, the almost reducibility just follows from the uniform hyperbolic theory. So the difficult case is that if this LE equals to L epsilon E equals to 0. So this is the subcritical case. In this case, we also call this conjecture the subcritical conjecture. And why this almost reducibility conjecture is important. So yesterday we said it because it implies that the subcritical can only support the purely absolutely continuous spectrum. But actually it's more because it is a powerful technique to deal with subcritical cocycles. So one can compare this with the techniques in the supercritical cocycles. A powerful tool is called a uniform large deviation. And for critical cocycle, a powerful tool is called renormalization. And for subcritical conjecture, the almost subcritical cocycle, the almost reducibility plays the same role as these two techniques. Okay. Okay, now let's introduce some progresses about this conjecture. Actually, the final answer to this almost reducibility conjecture depends on this arithmetics of this irrational alpha. So one can define a number by this irrational alpha. So just means if beta alpha equals to 0, in some sense we call this alpha Diophantine. And in this case, almost reducibility conjecture was first proved by for the almost Massive orbital, for subcritical almost Massive orbital, and for non-perturbative small like potentials. So this is Avila and Jetmiskai's work in 2010. And later, Avila proved that if beta alpha is larger than 0, then this almost reducibility conjecture is totally true for general one frequency shooting orbitals. So this paper can be found on the arXiv. But in if beta alpha equal to 0, then I will also announce that the almost reducibility conjecture is true for general one frequency shooting orbitals in 2011 or 2012. And he also presents the details in several conferences. Okay, but now it is still not on the arXiv. And today I will talk about a new proof, a different proof of the almost reducibility conjecture. So in the beta alpha equal to 0 case, in this case we use purely spectral method to prove the almost reducibility conjecture. As I said, I will present the details of his proof of the almost reducibility conjecture. And from those one can see it is a purely dynamic system method. But our proof is completely different. We use orbital duality and we involve almost localization to prove almost reducibility. So this is a different method. And this method to use almost localization to prove almost reducibility was first proposed by Avila and Jetmiskay in their paper and in their paper then proved that in general in the general case, if the potential is very small, so this lambda is very small, then one will have almost localization for the dual orbital. Then use this almost localization, one can use quantitative orbital duality, one can get almost reducibility. But our improvement here is that we do not need the smallness of the potential. We can prove that the dual of the subcritical case, the subcritical cocycle, for those orbitals, we will have almost localization. So this is a global almost localization result. Now, why we can prove this? Now I can explain the main ideas. So here is the sketch of the proof. So the basis of our proof of almost reducibility conjecture is from quantitative global theory. So as yesterday I proved, we present that this co-cycle alpha A is subcritical if and only if for its dual orbital all Lyapunov exponents are positive. Since all Lyapunov are positive, so one can expect some localization property, right? So this is why for subcritical, for the dual subcritical, one can prove almost localization because one have the positivity of Lyapunov exponents. So in this case, one can expect that almost localization holds. But the difficulty is the second step. Since the dual orbital, so we first consider the trigonometric polynomial case. Since the dual orbital here now is a finite range orbital, and this is the so-called band model. So for band model, if one want to prove localization just from positivity of the Lyapunov exponent, this is difficult because many of the previous results are under the assumption that there is a large computing lambda here. That is why Avila and Jepinskaya in their paper they only prove almost localization for lambda very small or for its dual lambda is very large. But here our new idea is to develop a method to prove localization or almost localization for the band model. Okay, here is the main theory that we prove that for this band model, if alpha is dimension and all Lyapunov exponents are positive, then one can prove this orbital will have almost localization for all theta. Okay, now let's give the details of to prove this result, because I think this method will hold in some very general case. One can consider some other models such as the random band model. Such method should also work. Okay, now let me sketch out the proof of Anderson localization or almost localization for the band model. So since there are many experts here, so actually one knows to prove Anderson localization for the band model, the most difficult part is to give upper bound of the numerator of the Green's function. So first, let me give the definition of the Green's function. So now let this Pi be the projection of L to Z to some interval I. So we assume this interval is of length Kd. Then this Hi is just some restriction of this band model to some interval. So one can write this Hi in this form. So here A, B are both D times C matrices. And actually we can view this Hi by taking the 2D boundary conditions. So we just need to consider solutions like U negative 2D plus 1 equals to U0 equals to 0. So we take these boundary conditions. Why I mention boundary conditions here? Because later we will see different boundary conditions are very important for my proof. Okay, the Green's function is defined in this way. So this is quite standard. You consider this the entry of the restricted orbital Hi minus E inverse. So the XY entry of this matrix. Then this Green's function has such a representation. So the denominator is the determinant of Hi minus E, but the numerator is some mu Xi is also some determinant. And the difficulty lies in that. So actually, for quasiperiodic orbitals, especially for this band model with cosine potential. So for this model, if the potential is cosine, then actually many years, I would actually maybe 10 years ago in Avila and Jepinskaya's paper, they already give a lower bound of this denominator. Okay, this lower bound is known for some non-random phases. The difficult part is to give an upper bound of this guy, or mu x1. And actually previously people only know how to give an upper bound of this mu x, y if one have some large coupling. And here we present a method that to give an estimate of this mu x, y, we only need to assume all level exponents are positive. So how to give this upper bound? We need to consider different boundary conditions. Okay, the boundary condition just
Lingrui, sorry to interrupt. I just wanted to ask a question. If you go back to the previous. So
okay.
my question, no, here. The Green's function. The formula of the Green's function.
A little down. Yeah.
So you said that, well, you have to estimate from above the numerator and from below the denominator.
Yeah, this guy.
To me, it's, I know how to do I know how to estimate from below the denominator in a perturbative way, but non-perturbatively.
Yeah. So that's the most difficult part, to give an upper bound of this mu x, y in a non-perturbative way. So you do not have any parameter lambda here. You only
I know, but what's the reference for this? For the lower bound on the denominator in a non-perturbative way, or what's some idea?
This is by this only holds for this cosine potential. That's the most that's the most important one.
Okay.
Okay. So if this potential is not a cosine,
you don't need
then the lower bound is out of reach. Yeah, this is already done by Avila and Jetmiskai in their paper. So this lower bound only holds for cosine potential. And so this upper bound, so our main difficulty is to give this upper bound of this numerator. And actually this upper bound of this numerator can be related to different boundary conditions. And recall that for our previous case, we only consider one case of boundary condition. Actually, we have 2D boundaries that we have 2D zeros on the boundary, and this boundaries can chosen to be anywhere, right? So we can assume we have some I1 to Rm and J1 to some Jm, and at the beginning we can assume we have 2D minus m zero conditions, and at the end we can assume m boundary conditions. Then we will have 2D boundary conditions, and that means we have we consider all boundary condition case. But why people do not consider this? Because for most of the boundary conditions, the corresponding truncated orbiter, this guy. So if you have this boundary condition, then you consider the truncated orbiter. For this guy, it is non-self joint. So this non-self, if we consider the determinant of this non-self joint orbiter, we have no idea to control the upper bound of this determinant, right? So here, our first idea is to give an expansion of this mu x bar y by this guy. So we only need to consider two kinds of boundary conditions. So the first kind is just means at the beginning we have d zeros. At the end we have d zeros, but this d zeros can be chosen to be anywhere. And the type 2 boundary condition is you consider d minus d plus 1 zeros at the beginning, and you consider d minus 1 boundaries at the end. So this is another kind of boundary condition. Then by pure linear algebra skills, one can expand this mu xy by these two kinds of determinants. So this T just means the determinant of some truncated orbiter minus E, the determinant of this matrix. And here, this I1 to Im and J1 to Jm are just some boundary condition. So the crucial thing is that mu xy, if you expand mu xy, then you can have a sum. And in this sum, there are only two kinds of boundary conditions. This is just means type 1 and type 2 boundary conditions. And these terms we have only finite many terms, and at most we have the terms have such an upper bound. Actually, we have a better upper bound. Anyway, the terms only depend on this d, so it does not depend here xy. It does not depend on xy. It can be any xy. So when we fix this dimension d, then you can view it as a constant. Okay, now the next thing is, if one want to estimate the upper bound of this mu xy, then we only need to estimate the upper bound of this G type 1 and G type 2 boundary, the determinant of G type 1 orbitals and the determinant of type 2 truncated orbitals. So we only need to give the upper bound of these guys. And how to give, so now how to give the upper bound of this G type 1 and G type 2? Actually, this proof is not difficult, it's quite easy, but this is a very, very beautiful observation that one can relate the determinant of this truncated orbiter with different boundary conditions to the sum of different Lemma exponents. So this follows from the definition of the Lemma exponents. Now let's recall the definition of the Lemma exponents. So why we have such idea? Actually, it comes from the 2×2 case. Recall that for 2×2 case, in the Green's function, actually we have some determinant, and for the determinant, if you want to estimate the determinant, if you want to estimate this determinant, then you can relate this upper bound to the transfer matrix, and you can use the Lemma exponent to control the entries in the transfer matrix. So you can use the Lemma exponent to control the upper bound of some determinant. But that is for 2×2 case, we only have the self-adjoint case. So the boundary condition is because the boundary, you have no choice in the boundary condition. It is clear. But for the band model, you have many choices of boundary condition. So we need to relate the determinant of different boundary or truncated orbiter of different boundary conditions to the different Lemma exponents. So that is from the definition of the Lemma exponents. So let's recall the definition of the sum of the first m Lemma exponents. We talked about this yesterday, and actually it is the weight of the iterated cocycle. So this a hat is the alpha a hat is the dual cocycle, and this is lambda m just means some weight. So this is weight m some transfer matrix is again some matrix. So if you want to consider the entries of this matrix, one can take some canonical basis of R2D, then one can consider its entries. So this delta I1 wedge delta IM, and here delta J1 wedge delta JM just means you take some entry of this matrix. Certainly, this entry can be bounded by the upper bound of these sums of gamma 1 to gamma m. So this is Simon's argument, the same argument. Actually, this is in quite generality. You can consider any ergodic or any minimal dynamics or any ergodic dynamics. You can give such an upper bound. Okay, now another important relationship is between this guy. This is the entry of this weight AKD, and this guy is the determinant of the truncated orbiter with some boundary conditions. And we have such a equality. So let's think about this. Just think about the 2×2 case. If we consider the iteration of the transfer matrix, then the entry of this transfer matrix equals to some determinant of the truncated orbiter. And in the band model, such relationship also holds, but it is more complicated because we have different boundary conditions. So this relationship is more complicated, but we also have such a equality. So you consider the entries of this wedge MAKD. So you have many entries. You consider one entry, then it equals to the determinant of the truncated orbital with this I1 to Rm, J1 to Jm boundary condition. And since, as we can see here, for this entry of matrix, we have an upper bound by the Lemma exponent. So for this the determinant of the truncated orbital, we also have such an upper bound. And in particular, why mu xy here for this band model mu xy, the upper bound is good because we do not need to consider all boundary conditions. So as I mentioned here, we only need to consider two kinds of boundary conditions. This kind is we have D zeros at the beginning and D zeros at the end. This guy is we have D plus 1 zeros at the beginning and D minus 1 zeros at the end. So we only need to give the upper bound of these two guys. And actually we have G type 1 have such an upper bound. In this upper bound, we have the sum of all Lemma exponents. But for G type 2, we have this upper bound. But in this upper bound, this is the crucial thing. In this upper bound, we only have the sum of first D minus 1 Lemma exponent. So gamma D is missing. So this is why combine the upper bound and the lower bound, we can get a negative gamma D decay because this G type 2, in this G type 2 upper bound, we missed the gamma D. So in general, if we consider this Green's function, we will have some gamma D decay. So this is why we can get this gamma D decay. Because in this expansion of mu xy, we only have these two types of boundary conditions. Yeah. Any question?
Yeah, what does this gamma D come?
Oh, gamma D is the minimal Lemma exponent.
I know, but so you have in the denominator you have the sum of the.
Yeah, in the denominator we have the sum of gamma D. Yeah. Then using this and this, we will get a gamma D decay. Yeah. So actually, this upper bound, you can see this upper bound is sharp because this decay rate is sharp for eigenfunctions, right? So yeah. So
I believe it cannot be better. What I wanted to see is why it is like this.
Which one?
Oh.
Oh, okay.
Okay, no. Okay, no, then I will continue. Okay. Yeah, this is the main difficulty to improve the almost localization, and then to pass from almost localization to almost reducibility is quite standard. You only need to use similar argument as Evelyn and Jeff discussed argument. You can get almost reducibility of the dual cocycle. Actually, so we have two remarks, and since the proof of this upper bound, actually we didn't use any feature. We just used some very common feature of the irrational rotation over the circle. So actually, this upper bound of the numerator of the Green's function holds in quite general for quite general base dynamics. You can consider screw shift or some other base dynamics. You can get similar upper bound, but the lower bound it depends on the lower bound of the denominator. It depends on the base dynamics to be irrational rotation and the cosine potential. So this is one thing. So we expect that such a method can also give a new proof of Anderson localization for random band model. Okay, for some other band models, and the key thing is to give the upper bound of this numerator of the Green's function. So that's the most important part. Okay, Now I finish the almost reducibility conjecture. I will talk about the next two applications. Okay, the next two applications is about the type 1 operator. Okay, what is the type 1 operator? Let me first give the definition of this operator. Okay, it is motivated by the almost massive operator. Recall that for almost massive operator, we have for all energy in the spectrum, we have three kinds of pictures of R epsilon E. One is of this guy, and so we have three kinds. We have three kinds of pictures, and there is a common feature that after you cross the first turning point, the slope is 1, right? This is a common feature for almost massive operator, and this is we plan to, our type 1 operator is to just consider the picture. Okay, we introduced the concept called the generalized acceleration. The generalized acceleration just means the slope of this R epsilon E at the first turning point. So this generalized acceleration equals to the acceleration in this subcritical, in this critical and the supercritical case, because the origin is a turning point. But in this subcritical case, this generalized acceleration does not equal to the acceleration, because for subcritical case, acceleration equal to 0, but the generalized acceleration equals to the slope of this piece. Why we consider this guy? Actually, later I will explain our intuition. Okay, as I said, so this generalized acceleration equals to acceleration in critical and supercritical case, and it equals to the slope of the first piece in the subcritical case. We introduce this. Now we can formulate the definition of type 1 operator. We say operator is a type 1 operator if the generalized acceleration equals to 1 in the spectrum. So from this definition, one can see the almost massive operator is a generalized, is the type 1 operator. So why we use this generalized acceleration? This is because of the following important proposition. We can prove that the type 1 operator is stable under analytic perturbations. So if we have a type 1 operator, then the perturbation, any analytic perturbation of this type 1 operator is still a type 1 operator. But if we only consider we only use acceleration, one will find that this acceleration is not stable under perturbation, because if you consider this critical case, then it can be perturbed to subcritical, and or it can be perturbed to subcritical case. Then acceleration can be 0, right? So, but general acceleration 1 is stable under perturbations. Okay, this is the type 1 operator. So the type 1, since it is open, so the type 1 operator will contain an important family of operators called the perturbations of almost massive operator. So if you consider the perturbation of almost massive operator, it is a type 1 operator. And for type 1 operator, one can look at the picture of this R epsilon E. It is different from almost massive operator, certainly, because one have many pieces in this slope, in this picture. For almost massive operator, we recall that we only have one piece. But the common feature is for the first piece, after the turning points, the slope is 1. So that is one common feature. But in some sense, it is more complicated because you have more pieces. And we consider this type 1 operator because we want to confirm our last expectation that only the first piece, the slope of the first piece matters. No matter you have how many pieces, the other pieces does not matter. So we will prove that actually for almost everything, we can prove almost everything, generalize almost everything about almost massive operator to type 1 operators. Okay. Now let me briefly give the main idea why we can deal with type 1 operators beyond. So because it is no longer self-joint, and it has many features that it will have many different features like almost massive orbital. But we find that the dual of type 1 orbiter is still very special. Okay, this is exactly our idea to build quantitative global theory, to use orbital duality to understand the original orbiter. So in particular for the orbital duality of type 1 orbiter, one will find the dynamics is more special in the sense that if you consider its dual orbiter, then you have a cocycle. This is a symplectic cocycle of dimension 2D. In general, it can be complicated, right? But yesterday we said it is a partially hyperbolic system, so it is not so complicated. But for the dual of type 1 orbiter, it is more simple because certainly it is a partially hyperbolic system. Moreover, the crucial thing is the dimension is not so complicated. The dimension of the center direction is 2. That's the crucial thing for the dual of type 1 orbiter. So that just means you can conjugate this cocycle to some block diagonal part. This is A plus, this is A minus, this is AC. And the A plus and A minus corresponding to some uniformly hyperbolic part, and AC corresponds to some dimension center direction. And this AC is the 2x2 matrix. So we can apply many techniques for 2x2 matrix to consider the type 1 orbiters. And with this observation, a very natural spectral consequence is for the dual of type 1 orbiter. So recall this is the finite range orbiter. And especially this orbiter has the spectral multiplicity of at most 2. So in particular, one crucial thing is this orbiter will have simple point spectrum. This will play a crucial role in our proof of contour spectrum. So in general, this is a 2D by 2D. This is 2D difference finite range orbiter. You cannot get the simplicity of the point spectrum, but for this dual of type 1 orbiter, you have the simplicity of point spectrum. So this enables us to consider the Tin-Martini problem. And this is joint work with you and Jitemsky. We proved that the Tin-Martini problem is robust. So actually, we can prove that the Tin-Martini problem is true for any type 1 orbiters, not just the almost massive orbiter. And the highlight here is that we do not need to assume this alpha to be rational, to be defining. It can be any irrational number, so it can be very, very Liouville. And we do not put any assumptions on the positivity of the lemma exponent, or so we can both deal with the subcritical, critical, and the supercritical case. So this is a monograph I posted yesterday that we can use different techniques in different regions to deal with the contour spectrum problem. Okay, before I sketch the proof, let's see some key ingredients in the proof of the Tin-Martini problem for the almost massive orbiter, and why these ingredients does not work for general orbiters. So one important ingredient is from Puig, so the so-called Puig's argument. The Puig's argument says that the almost massive cocycle cannot analytically reducible to identity. And here, the one crucial thing is that he used the self-duality of almost massive orbiter. So the dual of almost massive orbiter is also almost massive orbiter. So one can get the simplicity of point spectrum, then one can get such a result. And unfortunately, this argument breaks down for any other orbiters, because if the orbiter is not almost massive orbiter, then the dual orbiter is finite range orbiter or long range orbiter. One does not have the simplicity of point spectrum directly. So this is one important ingredient. Another two important ingredients about to prove K-matinib problem for all irrational alpha. Actually, one important thing is about Kutani theory. One can use this in the Schrödinger case. One can use contradiction argument. If the spectrum contains some interval, then one can use Kutani theory to get reducibility on some interval. Then reducibility in some interval will implies reducibility to some identity for some point. Then one can use Pugh's argument to get a contradiction. So one can combine Kutani theory and Pugh's argument to prove the K-matinib problem for not very Lewisian alpha. And for Lewisian alpha, the argument is quite different. It is based on some improvement of Choi, Elliott, and this guy. Sorry, I cannot pronounce this name. Yeah. And again, I would like to mention all these arguments include Kutani theory, Pugh's argument, or only works for almost massive orbital, because in all these arguments, one will use this self-duality. But if one think a little more, this self-duality is not essential. Actually, one need to use this self-duality to get some properties of the dual orbiter. And such properties of the dual orbiter, actually, in general, we prove that for the dual of type 1 orbiter, it will possess all these properties. Okay. So as I present as here, we can actually to prove the K-matinib problem for type 1 orbiter or for more general orbiters, there are two key steps. One key step is to deal with the Kutani theory for band model. Actually, one can say that Kutani theory for band model was already established by Simon and Kutani and Simon, but it is not satisfactory because one needs to assume all Llama exponents. So if Kutani theory contains two parts, one is about the essential support of AC spectrum. One is about the reflectionness. Actually, to prove the K-matinib problem, the reflectionness is more important. But for band model, Kutani theory, the previous Kutani theory only holds for in the case that all Llama exponents are 0. So in our paper, one essential improvement is to prove the Kutani theory for band model with just assuming 1 0 Llama exponent. So we do not need to assume all Llama exponents are 0. We only need to have 1 0 Llama exponent. Then we will have some partial reflectionness property corresponding to this 0 Llama exponents. And this is actually this actually holds in more general cases. We can prove this kind of Kutani theory for any partially hyperbolic system. So actually, the most important thing is to involve this partial hyperbolicity. Okay, this is an improvement of Kutani theory. The second thing is improvement, is some generalization and improvement of Pugh's argument. And we can prove. So I talked at the beginning that for the dual of type 1 orbiter, the point spectrum is also simple. So one can use this result to prove that the type 1 cocycle, the type 1 cocycle can also not be analytically reducible to the identity. So this is based on the generalization of Pugh's argument. Okay. Actually, this is not enough because the original Pugh's argument only works for Diophantine alpha. For Lewisian alpha, however, unfortunately, Choi, those three guys' argument does not work for band model. So instead we use a new method. We proved that we give an improvement of Pugh's argument. So in Peuk's original argument, he uses reducibility, but here we use rotation reducibility. So we prove that this type 1 operator cannot be rotations reducible to this rotation matrix with 0 average. And use this is actually some quantitative version of Peuk's argument. We can use rotation reducibility to get almost reducibility. Then we can get almost localized eigenfunction. Then we can use almost localized eigenfunction. We can prove the simplicity of this almost localized eigenfunction. So note that point spectrum is always simple because we have simplicity of the eigenvalues. Actually, if for one energy E, we have 2 different almost localized eigenfunctions, this is also impossible. And this kind of new arguments, actually, we are motivated by Ergodic Spectral's proof of the new proof of the non-critical dry-mathematic problem. But in our case, the proof is much more simple because we use Kutani theory to get rotation reducibility. From rotation reducibility to get almost reducibility is very, very easy. Okay. So this is about the chain mathematic problem. So essentially, we need these 2 arguments. Another thing is about the phase entry orbit phase transition conjecture. Right? And as I said, presented yesterday, actually this conjecture are related to subcritical, critical, and supercritical case. And the subcritical case follows from the almost reducibility conjecture. So now we already give the proof of this kind. So this is complete. This is clear now. And the critical corresponds to singular Canadian spectrum. This is totally open. We also don't know how to deal with this case. But for the supercritical case, to have arithmetic Anderson localization, we can first prove this arithmetic Anderson localization for type 1 operators. So recently, Han and Schrag they proved that if alpha is strong Fn and V is even, here evenness is essential for their argument. And they proved that this operator will have Anderson localization if the Lemma exponent is larger than 0 for almost every theta. This only for type 1 operator. And with this restriction on frequency and even the potential. And actually we can prove remove all restrictions. We proved that for any irrational alpha and any real analytic V, if the potential is a type 1 operator, one will have a sharp phase transition. Okay. So if LE on the set of LE larger than beta alpha, then we will have Anderson localization. And on the other side, it is proved by Ergodic you have purely singular Canadian spectrum. So for this type 1 operator, you will also have sharp phase transition. So the most difficult thing here is that you should not use the V. We do not assume V is even. This is very, very. If we assume V is even, then Han and Schrag use the standard Jet-Mescal argument to get such a result. But actually, if V is not even, this standard argument of Jet-Mescal's argument, the standard Jet-Mescal's argument breaks down because they only works for even cases. So we need to develop new ideas. Actually, we have 2 different proofs. So one is from reducibility. So our time is limited. I will only sketch here. So one method is from reducibility. One method is from okay. So one method is from reducibility. One method is from Jet-Mescal's the improvement of Jet-Mescal's argument. Actually, I remember that David asked me a question that if the dual of the positive Lemma of the operator of with positive Lemma exponent are subcritical, if we consider the dual of the positive Lemma supercritical region, if it is subcritical, actually it is subcritical. Actually, one can get more. One can have the. One can prove here. One can prove that this subcritical radius equals to the original Lemma exponent. So this subcritical equals to the original positive lemma exponent will give us a sharp reducibility result. Then one can involve this reducibility result. So one can prove such a reducibility result. Then one can use the reducibility to prove the dual localization. So this is one method to use reducibility to prove Anderson localization. So this will use almost reducibility conjecture. But we also have a proof. This is a more important proof. We have a proof to not use almost reducibility conjecture. We can combine orbitality and Jedrzejewski's method together to give an improvement of original Jedrzejewski's method to prove localization also for type 1 orbitals. And there is a possibility that such method also works for the orbital with acceleration 2 and even potentials. So this is a more quite, we need some new ideas to prove to in the second proof. Okay. Now I will just give a brief summary of my two talks. In general, my two talks, I want to give a brief monograph of this our work on quantitative global theory. Actually, we would like to say that quantitative global theory proves as a powerful tool to deal with various spectral problems, such as Andrew-Aubrey phase transition conjecture, the Martini problem, and also some quantitative calculation of the acceleration and some other objects. Anyway, it gives us more tools. The key in this tool is to involve orbitality. So so since orbitality, actually many years ago, people already know orbitality, but people do not investigate enough information from orbitality. So our project, the main contribution of our quantitative global theory is to fully investigate the orbitality, this tool, to use orbitality to give more tools to deal with the original shooting orbitals. And actually, from this orbitality, one can see that there is one more essential quantity than acceleration. So I would think the generalized acceleration is more important, because for subcritical case, this flat piece is related to, if you want to consider Andrew-Aubrey conjecture or Aubrey-Andre conjecture, it is only related to acceleration. But if one want to investigate the contour spectrum problem, one need some more essential quantities called the generalized acceleration. Okay. Since the subcritical case, the flat piece does not tell us anything about the contour spectrum. And why this type 1 orbital, we can deal with type 1 orbital, essentially because there is no double randomness. This is also a serious question. In which case can you give a lower bound of the Green's the denominator of the Green's function? So in general, one can give a lower bound of this denominator of Green's function if there is no double randomness. At least up to now. But so the essential difficulty for this field is that if the acceleration or generalized acceleration is strictly greater than 1. If it is 2, 3, or 4, how to deal with these orbitals? So one certainly needs to develop new tools to deal with this guy. But quantitative global theory also explains why, in this case, it is more complicated, because for the partially hyperbolic system, you will have 4 or 6 dimensional center. Okay, you have a more complicated center, so you need more tools to deal with this center. Actually, this is also so for partially hyperbolic system. In the dynamic system side, if the center is greater than 2, then people also don't know how to deal with this guy. This also explains if acceleration is 2 or 3 in the spectral side, why for many years there are no essential progresses. Okay, until now we proved something like that. So almost my field orbiter is some prototypical model. It is only one point if we consider the space of analytic functions. And type 1 orbiter, it contains the perturbations of almost Martial orbiter. So it is an open set in the space of analytic functions. So we generalize the properties of one orbiter to the orbiters, a family of orbiters, such that they form an open set. So the next step is how to if one can enlarge this set to be a more large set, or you can enlarge this set to the whole real analytic functions, the space of whole real analytic functions. So this is the main difficulty. There are many open problems in this region. Okay, I think I should stop here. Thank you so much.
Thanks a lot. Thank you for this talk. We have questions for Lingrui.
Okay.
Sylvius?
I was late, so I didn't see the statement, but you proved the conjecture for analytic or trigonometric polynomial potential.
Oh, you mean almost reducibility conjecture, right?
Yes.
Yeah. Actually, I proved for any real analytic case, and it is by trigonometric polynomial case approximation. We first prove this for what? So if we have.
Oh, okay. Yeah, I can see. I can see that this.
Yeah. So.
But then my question is the width. So in the definition of the almost reducibility, you said that there is this stronger version that has a constant width of analyticity for all ends. Do you get this uniform width of analyticity of
yeah.
or is it a weaker version?
Yeah. For analytic one, if this guy belongs to the analytic radius of this original function is h, we can prove the reducibility also in the strong case. But this h prime in this region, this h prime is much smaller than h. But this h prime is uniform.
But fixed for all ends.
Yeah. But fixed for all n. Yeah, this is from the strong almost reducibility in the local case. One can reduce the global case to the local case in a uniform band, and in the local case you will have strong almost reducibility. Then you will have a uniform band here. But in the trigonometric polynomial case, one can prove a stronger one. You can prove this h prime equals to h minus epsilon for any epsilon. Yeah, it's much. So you can shrink the radius for any small epsilon. Yeah. This is in the trigonometric polynomial case. This is for any real analytic case. Yeah.
Thank you, Sylvius, for the question. Do you have other questions for Lingrui? Well, let's thank him again. Thanks a lot for this presentation. We will reconvene at 35 for the second lecture by David.